Hello everyone, I'm Jiacheng, and together with my partner Shuaiqing, we are presenting our final project today. Our topic is the Brachistochrone and Titochrome problems. First, let me introduce the main problem and the basic background of our study. The problem of the Brachistochrone is to find the path between 2 points in space such that the time taken for an object to fall from the starting point to the end point along this path is minimized, with the only external force acting during this process is gravity. According to Bernoulli's work, the sigmoid formed by the rolling of the circle is an ideal analytical solution. Regarding our work, the first thing we need to do is find the shortest time path between 2 points through our code. We know that the circle forming the sigmoid moves at a constant angular velocity, which in our physical scenario is the square root of g over r. Therefore, we have these equations. We also added a straight line for comparison to let everyone know that the shortest time path between these 2 points is not a straight line. The coordinates corresponding to the straight line are expressed by these formulas, where theta is the angle traversed by the circle during rolling. We set the starting point at 0.0, where the endpoint can be adjusted by interactive buttons. Here is a comparison of the straight line and sigmoid first. Below are the position of two objects at the same time on the straight line and sigmoid respectively. Here we change the coordinates of the endpoint to see the simulation effect. We can find that the point on the sigmoid always reaches the endpoint first.
Hello everyone, I'm Shuaiqing. Now let me introduce the initial idea Bernoulli had when he first studied this problem. We know that during the following process, the object will continuously change its speed. With the concept of calculus, we can divide the vertical distance from the starting point to the end point into many small layers with equal height, and assume that the speed is constant within such layers. We can refer to this image. And this situation is very similar to the behavior described by Snell's law. Also, according to the conservation of energy, we know that the speed between different layers can be expressed in this formula. Combined with Snell's law, we can use this formula to express our coordinates in space. For each layer of equal height, our code will displace the numerically calculated cycloid and Snell's law approximation cycloid on the graph. We can change the interaction button here to fit the curves. We can find that Snell's law can simulate the Brachistochrone very well. In addition to Brachistochrone, our study also includes the Tactochrone. Different from Brachistochrone, the Tactochrone problem finds a curve such that from any point on the curve at the starting point, the object can move to the lowest point of the curve in the same time interval. The lowest point of the cycloid always corresponds to the theta equal to pi. here. And since we only concern with different starting point on the same curve, we directly set the radius of the circle to 1. The image generated by our code can display this situation. Here we set different starting point for several objects on this curve, and then let them start moving at the same time. We can find that they always arrive to the end point. We can find that they always arrive at the endpoint simultaneously.